The aim of our research work is combat 4-port MIMO antenna Diplexer utilizing slotted half-mode SAW technology. Our presentation will cover the following sections. Introduction. In recent years, multiband antennas have been widely utilized in compact systems and wireless communication. Traditionally, a deplexer is used to separate transmitting and receiving signals. However, self-deplexing antennas can naturally perform this function without extra components. This makes the system simpler, more compact and efficient. Increasing the channel capacity improves the wireless coverage and ensures a strong, reliable connection in dynamic environments. To address these challenges, this work presents a novel and compact 2x2 MIMO self-deplexing antenna based on half-mode substrate integrated waveguide technology. Figure 1 shows the proposed 4-port 2x2 MIMO antenna deplexer yielding at two different frequencies. The antenna is fabricated on Rogers RT-Durite 580 substrate with a thickness of 1.575 mm. The SAW cavity is constructed using the chains of metallic wires that serves as a lateral walls of planar cavity. These wires effectively form the metallic boundaries of SAW cavity within the substrate. Initially, a full mode SAW cavity is excited via a coaxial fluid. The dominant TE110 mode is achieved at 5.2 GHz. When port 1 and port 2 are excited, two half mode SAW cavities resonate at 4.9 GHz and 5.8 GHz. By placing the rectangular slot at the center of the cavity, 50% of bandwidth is achieved. When port 1 is excited, the TE110 mode split into half TE110 mode resonated 4.85 GHz and another half TE110 mode resonated 5 GHz. When port 2 is excited, odd even modes of cavity resonated 5.7 GHz and 5.85 GHz. Different cavity elements are placed orthogonally, achieves a high isolation greater than 45 dB. Slot initiation enhances the bandwidth but reduces the isolation by approximately 8 dB. Frequency selective radiating elements are placed orthogonally, sharing the electric walls. These setups after the same frequency fields causing the dips in S13 and S24 at operating frequencies that is shown in figure 4. Figure 5 shows the S parameters versus frequency with the length of the slot is varied, increase in the LS1 or LS2 leading to the downward shift in resonant frequencies and effect in the impedance matching across both the frequency bands. Figure 6 shows the S parameters versus frequency with the variation in slot position. If the slot position is varied independently while keeping the other fixed, the port position influences the mode coupling in both the lower and upper frequency bands, making it a critical factor for optimal impedance matching. Figure 7 shows the S parameters versus frequency variation with the change in the cavity gap and the effect of the cavity size. Increase in the G1 alters the mode coupling, leading to the enhanced bandwidth across the upper and lower frequency bands, that is shown in figure A. A larger cavity results in a downward frequency shift due to the enlarged effective aperture, which extends the current path, that is shown in figure B. MIMO diversity matrix. The proposed 4-port antenna achieves an enough correlation coefficient that is less than 0.05 across both the frequency bands, and the diversity gain is less than 9.8 dB in both the frequency bands, that is shown in the figure 8. The proposed antenna maintains the total effective reflection coefficient that is minus 12 dB across the operating bands, and it maintains the channel capacity losses less than 0.1 bits per second per hertz across both the frequency bands, that is shown in figure 9. Figure 10 shows the photographs of the fabricated phototype front view, bottom view, simulated and measurement results and radiation patterns. It exhibits a stable bandwidth and gain performance. When port 1 is excited, the measured bandwidth is 150 MHz. For port 2, the bandwidth is 250 MHz. The measured gain ranges from 4.8 to 5.2 dBA when port 1 is excited and 5.59 to 5.86 dBA in port 2. The radiation pattern shows the front to back ratio exceeding 10 dB in both the bands. The copole to cross polation ratio is greater than 17 dB in YZ plane and 11 dB in XZ plane. Conclusion. This article presents a compact 4-port self-deplexing MIMO antenna designed for wireless LAN and ISM band applications. By utilizing TE110 mode and half-mode SAW techniques, the design achieves a 50% size reduction. Radiating elements positioned out of the phase effectively cancel the field coupling, resulting in isolation exceeding 30 dB between any two ports. MIMO performance metrics ECC, MEG, CCL, and TARC are found in the satisfactory limits. The proposed antenna features a simple low-profile configuration with self-deplexing capabilities, offering dual-channel capacity in both the frequency bands. Its compact design, reliable communication, and superior radiation properties makes it ideal for dense wireless communication networks. Thank you.